Crafting a testable experimental hypothesis. Welcome to our step-by-step guide designed to help you formulate a testable experimental hypothesis. A hypothesis is a foundational element of scientific research, predicting the relationship between two variables, the independent variable, IV, and the dependent variable, dV. Let's break down what these terms mean and how you can use them to ensure your hypothesis is ready for a true experiment. Firstly, a hypothesis must be specific and clearly articulate the relationship between the IV and dV. The IV, or independent variable, is the factor you manipulate or change to observe its effect. Think of it as the cause. The dV, or dependent variable, is the effect or what is being measured as a response to changes in the IV. Start by identifying your IV. Ask yourself, what am I testing or changing in this experiment? This could be anything from the amount of light a plant receives to the type of learning method applied in a classroom. Next, define your dV. This is the outcome you're measuring, which might vary based on changes to the IV. It could be the growth rate of the plants or the test scores of students. Data analysis. To analyze your data effectively, you'll need to organize it in a spreadsheet. This includes categorizing your experimental and control groups, often represented as binary measurements like true, false, or yes, no. Measuring your variables. In scientific research, especially within the realm of criminal justice, the precision with which you measure your variables can significantly impact the validity and reliability of your findings. Both the independent variable, IV, the factor you manipulate, and the dependent variable, dV, the outcome you're measuring, must be quantifiable. This means you need to have a clear, objective method for measuring these variables, allowing you to analyze your data accurately and draw meaningful conclusions. Let's explore how this principle applies through a criminal justice example, detailing the measurement process for both the IV and dV. Example: studying the effects of patrol strategies on crime detection rates. Independent variable, IV, type of patrol strategy implemented, e.g., fixed, random, or hotspots policing. Dependent variable, dV, crime detection rates in the patrolled areas. Measuring the IV. To quantify the IV, you can categorize each patrol strategy into distinct groups, e.g., 1 for fixed, 2 for random, and 3 for hotspots policing. This numerical representation allows for easy analysis and comparison of the impact of different strategies. Measuring the dV. The dV can be measured by the number of crimes detected or reported in each area during the implementation of the patrol strategies. This measurement could be a simple count of incidents or a rate per 1,000 residents, providing a clear, numerical indication of the strategy's effectiveness. Manipulating the IV. In a true experiment, the heart of the scientific method lies in your ability to control and directly manipulate the independent variable, IV. This manipulation allows you to observe whether it causes any changes to your dependent variable, dV. In simpler terms, you're setting up a scenario to see if changing one specific factor, IV, directly affects another factor, dV, in the way you predict. Randomly assigning subjects to experimental and control groups is a crucial strategy in this process, ensuring that any differences observed are due to the manipulation of the IV and not other variables. Let's expand on this concept with another criminal justice example. Example: the effect of lighting on public safety. Independent variable, IV, the level of street lighting in public areas. Dependent variable, dV, the incidence of street crimes, e.g., theft, assault. Manipulating the IV. To investigate the impact of street lighting on public safety, you could increase the lighting in certain areas, experimental group, while keeping the lighting in other similar areas unchanged, control group. By randomly assigning different public areas to either have increased lighting or serve as a control with no change in lighting, you can directly assess the effect of lighting on crime rates. This setup allows you to see if better lit areas experience fewer street crimes compared to less lit areas, directly linking changes in the IV, lighting, to changes in the dV, crime rates. In the example, the key is the deliberate and controlled manipulation of the IV to observe its direct effects on the dV. Random assignment is crucial here. It ensures that each group is comparable at the start of the experiment, thereby increasing the likelihood that any observed differences in outcomes are due to the manipulation of the IV rather than other factors. This methodological rigor is what defines a true experiment and allows researchers to draw more reliable conclusions about cause and effect relationships. Control groups. A control group is essential for comparing the effect of the IV against a group that hasn't been exposed to it. Define what business as usual will look like for your control group, ensuring they do not receive the experimental treatment. Final hypothesis statement. To conclude your experimental planning, it's crucial to articulate your final hypothesis in a straightforward, succinct manner. This statement is essentially a prediction you're making about how altering the independent variable, IV, the factor you're experimenting with, will impact the dependent variable, dV, which is the outcome you're measuring. Your hypothesis should bridge the IV and dV in a cause and effect relationship, clearly indicating the expected change or effect. Let's translate this into plain English. Your final hypothesis is like making an educated guess. You're saying, if I change this particular thing, IV, then this other thing, dV, will react in a specific way. Here is an example from the field of criminal justice that meet all the criteria we've discussed. Example 1. The effect of community policing on crime rates. Independent variable, IV, the implementation of community policing strategies. Dependent variable, dV, the overall crime rates in the community. Final hypothesis statement. Implementing community policing strategies causes a decrease in the overall crime rates in the community. This hypothesis predicts that by changing the policing strategy, IV, there will be a specific effect on the crime rates, dV, which is expected to decrease. The experiment would involve comparing crime rates before and after the implementation of community policing in a controlled manner to observe the cause and effect relationship. This example clearly states the expected relationship between the independent and dependent variables, adhering to the principles of crafting a testable and concise hypothesis. This process lays the groundwork for conducting meaningful and reliable scientific research. Thanks for watching.